Welcome to AZR115, building an Azure mobile app client. So by now, you'd have already gone through the Azure 101 class, where you learn about the Azure platform and how it can be used, as well as the Azure 110 class, which showed you how to develop the server-side configuration for your mobile app service. Now in this class, we're going to take the next step of connecting the Azure app client through to the server, just so we can take full advantage of the Azure infrastructure. My name's Glenn Stevens. I'm going to be your instructor for this recording today. Now, if you have any questions post-class, feel free to use the contact details that you can see on the slide, or alternatively, you can post a question to the Xamarin forums, or schedule an office hours with one of our many awesome Xamarin University instructors. All right, let's get started. Now again, this video is a continuation of the Azure 110 class where we built the backing service. And today, you're going to learn how to build a mobile client that connects to an Azure service, that reads and writes to a database and manages scenarios when your device is offline. By the end of the class, you'll have created a mobile application that can perform the CRUD operations, the create, read, update, and delete, to a database that's hosted against your Azure service. In the previous class, Azure 110, we set up the server side, so let's now turn our attention to the mobile app. In this section, we're getting the fundamentals for our client in place. We'll be adding in the appropriate NuGet packages for the Azure work. We'll be connecting to Azure and ensuring we have the configuration correct in order to establish our connection to your Azure service. Azure App Services supports a mobile app service model, which provides access to data, authentication, and push notification services. And it's the server that decides which features it wants to use from the Azure App Services platform. Now, the mobile client utilizes standard web protocols to access and interact with the service. We cover the server side of this diagram in Azure 110, and this class is going to dive into the client side, how to consume the services exposed by Azure. Consuming data on your .NET or Xamarin application is pretty easy, as the mobile app uses standard HTTP or HTTPS using REST to interact with clients. So as long as you know the endpoint location, you can interact with the service. So if you've taken the AZR115 class, then you already know how to access and work with the service. So here you can see we're creating a new HTTP client, setting our accept type header, and issue a GET against our Azure service endpoint. And it's going to return JSON data, which can then be passed by the .NET code. Now there's actually two types of mobile services available from Azure. Now the latest version of Azure Mobile Services is the Mobile Apps feature Azure App Service. And the older version, which is now deprecated and unsupported, is the Mobile Services API. Now it's important to note that these two are not compatible with each other. So Azure uses a special header value passed from the client to determine the expectations and the version, and that's Xumo API version. And it can be either passed as a header value with each request or on the URL, like you can see here. And the value indicates the version of the client SDK being used. And Azure expects version 2.0.0, and all other values are going to return a 400 level bad request response. So this version check can be disabled on the server side through a web.config setting. So when dealing with the data, you'll find it's passed to and from the server in the standard JSON format, and the client can use any available parser or even just work with the strings directly. Here we're using the popular Newtonsoft JSON.NET parser to take the returned JSON string and turn it into a .NET object that we can use the C# dynamic support to work with. Now, of course, if you know the shape of the data, then you can use the generic form of the deserialize method to return a known shape. While you can do all the parsing and connection using the standard networking classes, it turns out that Microsoft publishes a set of client SDKs to interact with mobile apps on the Azure App Services platform. So it does all the necessary work on your behalf to connect and communicate with the backend service. And on .NET and Xamarin, it utilizes HTTP client and JSON.NET, the very same mechanisms that we use. And there's SDKs for most platforms, including .NET, HTML, native iOS and Android, and of course there's a Xamarin SDK, which is what we're going to be using today. Now the SDK provides support to access all of the features of the mobile app service. For example, it has methods to authenticate against third-party OAuth providers and negotiate that with Azure with a single line of code. And you'll see that in the upcoming class on authentication in Azure. So we're going to focus on consuming and manipulating data exposed by an existing Azure service in this video. And the other two topics we'll actually cover in later classes. Now there's 3 steps we have to do to our application to add support for the Azure Client SDK to our Xamarin app. So first we'll need to add the Client SDK assemblies, and these are shipped as NuGet packages. So by now you should already be familiar with NuGet. If you're not, I'd suggest taking the AZR115 class, Introduction to Cross-Platform, where we look at that topic in more depth. Next, we'll initialize the Azure SDK, and this has to be done in the platform-specific projects. And then finally, we'll configure and use a mobile service client object, which is an Azure SDK type to connect and talk to our Azure mobile service. So let's go through these steps in detail. .NET-based apps, which include Xamarin, can use predefined classes to consume Azure services. So while you can add a binary to your app from a local DLL, the most common way to add support for an Azure service is through a NuGet package. And there's a ton of these packages online. Many are marked as deprecated as Azure has evolved really quickly. So you can use the feed shown in the browser to get a list of Azure SDK packages. And these libraries are provided by Microsoft and are all open source, and you can find them at github.com/Azure. The primary package we want to add is the Microsoft Azure Mobile Client package. And this is the core assembly that contains the required initialization and all of the support to interact with. And this will add a few other dependencies such as JSON.NET to your projects. And Azure Client SDK and dependencies are distributed across a variety of assemblies. So you should also make sure to update these dependencies just to ensure you're getting the latest distribution. And you'll also want to add this package to each of the platform-specific projects, iOS, Android, and Windows, as well as any other project that'll be using the Azure types. Now, once you've added the package, we need to add a single line of code into our Android and iOS applications to initialize the framework. And this code has to be executed for each launch. And on Android, it's common to either place this in your onCreate override of the main activity for Xamarin Forms or in an application override in a Xamarin Android application subclass. The key point here is that it gets executed just once, and it has to be executed before any other Azure code. On iOS, it's common to place this into your finish launching method in the app delegate. And this initialization is only required for Android and iOS apps. Windows apps don't actually require this code at all. And once we've added the NuGet packages and completed the platform-specific requirements, we're ready to connect to the Azure service. And we can do this with a mobile service client object. And this is a built-in type in the Azure SDK. Now, the constructor takes the Azure service endpoint, which is the URL from our app dashboard. And this object wraps a HTTP client object and provides the structure for the HTTP requests, which will be made to the service on our behalf. Most of the time, you should create this object when you're ready to use Azure features and then keep it for the life of your application. And it'll open and close network connections as needed. Okay, so it's time for the first exercise where we'll set up our application to use Azure. Now, in just a moment, pause the video and then follow the instructions in Lab 1. And once you finish the lab exercise, resume the video and then we'll review the steps. So let's do a quick review of that particular lab exercise. Now, fundamentally, the first thing we need to do is to add a reference to the Microsoft Azure Mobile Client package. So we just add those from NuGet. And not only do you add it to your shared code, like the portable class library we have here, but we also need to add it to our Android and our iOS and Windows projects. Obviously, because I'm using Xamarin Studio, I can't add it to the Windows projects. But if I was using Visual Studio, I'd add it in there as well. Now, the second thing we need to do is we also need to initialize the iOS and Android projects. And you'll notice here I've got my main activity for my Xamarin Forms project, and I've got a line of code here called microsoft.windowsazure.mobileservices.currentplatform.init. And that actually does the setup for Azure Mobile Services for that platform. You'll find one on the finish launching method of your app delegate for iOS as well. So here we've got the same call to Microsoft Windows Azure.mobileservices.currentplatform.init. Now, in addition, we've also got this great file here, the iSurvey question service. And this is actually what's doing a lot of the work in order to manage the survey for us. So we've got a survey app. You would have seen that when you ran. And it's basically talking to this interface. All it's got is things like add or update a survey response, how to delete a survey response, getting the questions, getting the responses for a survey, and getting the response for a survey. And you'll notice they're all asynchronous methods returning a task or a task of a particular type. Now, within the application in the first lab, you'll see that we've got the mock survey question service. So this implements really just a local implementation of this particular interface. But what we want to get to is really where we use the Azure service to connect those parts. So here I've got the Azure survey service, implementing iSurvey question service. We've got our connection, so we've got our mobile service client, and we're creating that, but only creating if it hasn't been created before. That's the purpose of this initialize method. So have we created the client before? If we have, then jump out of that method. If not, go ahead and create one. And then before every other method call, we want to make sure that we're using the Azure mobile service client. So we call initialize. Now, right now, this is not implemented fully, but we'll be implementing more and more of this class as we go through. And also on our main page.xaml.c#, you'll notice in our iSurvey question service, instead of creating a mock survey question service, we're now creating the Azure survey service. So now we've completed the foundations of our Azure app, and we've added the NuGet packages needed to connect to Azure. We've configured our app to connect to the server and then connected into the service. And now that we have our app configured, it's time to start pushing and pulling data. So let's go through the next series of steps. We've got our database that's been generated in the server, and we're going to now try and connect in. And when an Azure service exposes a table for a mobile client, it does it by opening an endpoint on the server using the /tables prefix with the name of the table that it's interested in. And the mobile client sends standard HTTP requests to the server, which then turns those into database queries based on the HTTP verb. And the server identifies the operation being performed based on that verb, and then it issues an asynchronous operation to the database against the table identified by the endpoint. The database then returns a set of rows or a row count based on the operation, and the server will then translate the resulting data into a JSON response and then send it back to the client. And every operation you do against a table results in a network flow that's very similar to this. So let's look at how we issue these calls in code. To access an exposed table from your Azure service, you'll need to use an iMobile service table interface. And this represents a single table endpoint and has all the methods on it to read and write to the table. And as with a mobile service client, you generally will get the table interface and cache it off in your app to access the table data. You get this interface through your mobile service client object and the getTable method. So you have to supply the table name, which is appended to the URL endpoint to identify the specific table to work with. You can then execute methods on this table to get, insert, update, and delete data from the server-side database table it represents. So here, for example, we're retrieving all the records with a built-in method named readAsync, walking through all the returned records and accessing an ID property on each one. So notice, just like before, we're using the dynamic keyword to get the ID value. And this type being used here is a J object, which represents a JSON data blob. The ID property that we're accessing on these records is a standard part of the table structure returned by every Azure App Service mobile app table. And it represents a primary key on the table and is by default a string type. And there's 4 other values you can expect to see for every table as well. And these values are used for synchronization with the server. There's the created at, updated at, version, and deleted. Now, created at represents the date and time the record was created. Updated at represents the date and time the record was last updated. The version represents a base 64 encoded string that represents a unique version. And deleted, well, it's a boolean that represents that the record has been deleted. The deleted and the version are actually used to support offline synchronization. So these columns are server generated and populated by default. Now, clients can access this data, but really you should consider them to be read-only. The dynamic support in C# is very convenient, and especially if you don't know exactly what the shape of the JSON data is, it can actually be a quick and easy way to work with that data. However, it does have a runtime cost both in performance and memory because it relies on runtime interrogation of the object in order to retrieve the data. Now, it also lacks IntelliSense, which makes it easy to accidentally misspell a property value and cause a runtime failure.
Now instead, like most developers, we prefer to work with strongly typed data. And if you know exactly what you're working with and know what fields you want to use in your client application, then you can create a data transfer object, also known as a DTO, to represent the data. And this is where we define a .NET object that conforms to the shape of the JSON and has public properties that match up to the expected fields in the JSON object. And we can then use a JSON parser like the Newtonsoft.json library to convert our object to and from JSON. But it turns out that the mobile service client has this support built in. GetTable has a generic version which takes the defined DTO to work with, and under the covers the methods will now use the Newtonsoft JSON.NET parser to turn the JSON data into the specified DTO type. And this allows us to work completely with strongly typed data, and notice that it now returns a collection of our DTO objects and that we get full IntelliSense when we interact with the data. Now using this variation is preferred over working with raw JSON types if possible, because it enforces the expected data between the client and server and reduces the risk of runtime exceptions due to missing or misspelled data. So let's actually talk a little bit about defining a DTO. The one property you absolutely must define in every DTO is the ID property, and this is the primary key on the table, and it's used in almost every operation to identify the record that we're working with. For example, when you update the record, the ID property is used in the server-side where clause to identify the record being updated. As mentioned earlier, the server will populate this field even for insertions, but from the client side, we should consider this really to be a read-only value. The JSON.NET parser by default will match properties in the DTO to values in the JSON using the property names. And it ignores cases for these matches too. And that means you shouldn't have two properties with the same name that differ only in case. Here we defined a new property named text, and that'll be matched to a text value in the JSON data structure. You'll notice in the JSON data structure, text is actually all lowercase. And if the value doesn't exist in the JSON object, then it'll be ignored and left in a default state, which will be null. If you want to change the name of the DTO property to something more relevant to your client-side code, you can apply a JSON property attribute to the property and specify a different name. And this is used for both serialization as well as deserialization. Here we're using the attribute from the Newtonsoft.json framework because that's the parser the Azure SDK uses. However, the parser also knows about the system.runtime.serialization attributes used by the data contract framework that was introduced in WCF. So if you already use these attributes, then the parser will respect those values. And for example, here we could use a data member attribute to change the name of the serialized property. As shown earlier, you can access the other built-in columns if desired by declaring fields in your object to capture those values. And this is completely optional, and if you don't use these fields, then you don't need the properties. And the same name matching technique is used, it's just a JSON value after all. However, you can also apply some other built-in attributes to ensure the name is matched properly. So it matches up version, the created, and updated dates. So these are just custom versions of the JSON object attribute that we saw with the name pre-populated. And it's useful to use these if you want the system supplied fields just in case they ever change the default name of the field. And keep in mind that this only matches up to the default name. If the server changes, then these attributes won't apply. Remember that these values are really intended to be populated by the server side. You generally should really avoid changing them. But they must have a public setter so the parser can set them. If you want to define client-side properties on your DTO which shouldn't be sent to the server, then you should decorate these properties with a JSON ignore attribute. And this is useful for client-side values that are created and used only by the client side. For example, here we've got a title, which might be the first 10 characters of the entry, or you might have a property that concatenates two other properties from your DTO. Now when this attribute is present, the parser will skip over the property. Even if the value is present in the JSON data, it won't be filled in. This attribute is particularly important when sending a DTO up to the server, since it will by default serialize all public properties into the JSON blob. One interesting thing to notice when getting the table interface using a strongly typed DTO is we don't supply a table name like we did with the non-generic version. Now instead, the table is identified using the name of the DTO itself. And here we would issue calls to the tables/diary entry endpoint. And on the URLs are case insensitive, so this would match /tables/lowercase diary entry. However, we often want to name our DTO using .NET conventions, and our tables are often defined in SQL terms, which don't always line up. For example, what if we named our server-side table entries? If we issue this request, we'll get a 404 or not found error because there's no diary entry table exposed. We can break this relationship the same way we customize the property names, through an attribute. And in this case, it's the JSON object or data contract attribute. So we specify the specific table endpoint name as part of the attribute, and it'll change the URL. Finally, one other customization point is the parser itself. And when you create the mobile service client, you can set some additional properties on it. One of the most common is the serializer settings property. And this allows you to customize how the JSON parser works with the data being sent or received from the service. For example, you can change how casing is handled, how dates are handled, or how missing fields in the data are also processed. In this next exercise, we'll be customizing the DTOs for our survey service. Just like before, in just a moment, pause the video and then follow the instructions, this time in Lab 2. And then once you finish the lab exercise, resume the video and then we'll review the work done.
Now for this next lab, our purpose is to actually look at the structure that we have coming back from our Azure service as JSON and actually work out how to create the C# DTOs for that particular JSON. And you can see some examples here. We've got the tables/questions and the tables/responses. And we need to create the appropriate mapping. So we've got the ID, version, created at, updated at, deleted, and the answers in the text. Now the main information that we're using for this particular item is ID, answers, and text. That's for the questions. And for the response, we've got ID, answer, question ID, and name. Now the two classes that we've created are really the survey question and the survey response. And if we look at the survey question, we can see we have that ID. And remember, all the Azure Mobile Services classes have that ID, and that's a string. We've also got the question, and you'll notice the question is the name of the property, but the actual JSON element is called text. So we're using this JSON property from Newtonsoft's JSON.NET in order to say, well, when it's loading it from the JSON, that's really what we're referring to. Likewise, there's another property for the answers, and we've also added just a two-string overload. Now we've also got the survey response, and we've got a few things happening here. Of course, we've got the ID again. We've also got the question ID, so that's the name of the element coming back from JSON, but we've decided to call that property name survey question ID. So it'll know how to really persist to JSON using that question ID instead. We've also got the name and also the answer, which is just a response index. So our classes are actually a lot more C# friendly. Even though we're returning the JSON, our classes reflect the true intention of what we're trying to do. And there's also the updated at, so we're getting a reference to the updated date for that last particular record as well.
The mobile service table interface exposes a set of methods that are used to perform create, read, update, and delete operations on the server data. And as you know, these methods are internally mapped to HTTP requests sent to the server, where they're then mapped to SQL statements on the server side. So we have the insert async method that'll insert an item into the database on the service. We have the update async method that'll update an item on the server. The delete async method performs a delete operation where the read async will return the items from the server, and the lookup async method returns a single entry from the server. Now let's look at some examples of using these methods. First, we can add new records to the table through the insert async method. And this takes a DTO object, which is the object to insert. And remember that the DTO must have an ID property. And you should also notice that it's async. All Azure service calls are asynchronous in nature because we're talking to a web service. So keep in mind, you should never forget that this is a network operation. And the await completes when the server side is finished and returns the JSON response. System fields, they're filled out by the server side and returned once the operation is completed. For example, the ID will be filled in once the operation actually completes successfully. So also notice that we've wrapped the call in a try catch. And this is also important. The operation could fail for a number of reasons, and this error will be turned into an exception, and we should manage this error within our app. Update and delete are similar to insert, except for the operation they perform. The syntax and usage is identical. We pass an item that we want to update or delete, and then again in this example, ensure that we're protecting the code with a try-catch, as again, this is a network operation. And finally, we come to retrieving data. And this is probably the most common operation, especially for apps consuming data, and as a result, there's several ways it can be performed. Now, the first approach we can do is to retrieve all records from the server, and this is done with the read async method. So the read async method you see on the screen is essentially equivalent to a select star operation in SQL. Now, this returns an enumerable collection of DTOs. Alternatively, we can scope our result to a single record using the lookup async method, and this takes an ID to retrieve and returns one record.
These two operations represent an all or single record approach, which works for some scenarios. But what if we want more than one record, but not all records? For example, let's say we call read async, and this causes the server to do a select star from the database. And the server retrieves 1,000 records from the database, allocates a big JSON block, and passes it back to the client. And then the client iterates through the data and displays just a subset, so 10 records, for example. And this is really a horrible use of resources. Not only will it take more time to complete, but we're also wasting memory, network resources, and database time. Instead, we want to push that filtering up to the server where it belongs. And in this model, the client would somehow provide a filter as part of the query to read 10 records, and the server would then use that filter in the database query it issues. Then the database server would return 10 records, the server would package that up into JSON, and then return it to the client, which would then display the records without filtering. The secret to this query filtering is the OData specification. And recall that we said that the Azure service implements an OData endpoint to front-end our database. OData is a standardized data query language intended for web services. And the Azure mobile service supports a subset of the OData version 3 specification, and the client passes these as part of the query string to retrieve the data. The iMobile service table interface has a set of methods to create a query. That query is represented in another interface, iMobile service table query. And the query methods provide for standard querying filters such as where, order by, skip, and take. And you'll notice that each query function returns the query, and that allows for a nice fluent syntax. And in addition, the method names conform to the link standard. That means you can use the link query language to construct those queries. Before we dive into the query usage, we have one thing that we need to talk about. And the query itself represents an expression that can be passed to the server to execute. However, creating a query doesn't execute it directly. Instead, once you've constructed a query, you have to send it to the server for executing. And this is typically done through one of four methods. First, there's the toEnumerable async method, and that'll return an IEnumerable of a generic type T. And this is the same as executing the read async method. We have the toListAsync method, which returns the data as a list of generic type T, which is often an easier collection type to work with. There's also the toCollectionAsync, which returns a collection and allows you to return a page dataset so you can receive information incrementally if you need. And if you're on the Windows platform, you can also use the toIncremental loading collection, which will let you download DTO objects as you're accessing them. It's really impractical to pull down all the data for your table to a mobile device. It'll take a lot longer than you need, and often you only want a subset of the data anyway. So let's look at some of the basic mechanisms for this to work. And we'll start with the most common query style, the where clause. And this allows you to filter your query to a subset of records based on a past condition. And the condition is a C# expression that supplies simple evaluations which will be done by the server. So there's things like the equality operators, greater than, less than, and there's also contains. So in addition, there's also a few modifiers you can supply to the query. For example, toUpper and toLower are supported to force a case-insensitive query. And here we've got a query being created which will restrict our records to the ones that contain the word secret in any case. When we send this query to the server, it'll add a filter expression to the get statement, which the server will turn into a where clause that passes to the SQL Server. And you can see here that the $ filter is being used, and the $ filter is a standard OData keyword, and it's the substring of and to lower operators. Notice that the end of our query is a to enumerable async, and this is actually what finally processes the query and sends it to the server. Another common desire is to restrict the return data, not by filtering, but by the columns, and this is accomplished with the select statement, which creates a projection of the data. As with the where clause, the select statement is somewhat limited compared to link to objects. It can only contain columns known to the server, and other elements are either performed on the client side if possible, or generate a runtime error. And when this is executed on a server, it'll generate a select query parameter for the server to process. You can see an example of that down the bottom of the slide. And this is what in turn will restrict the generated SQL select statement. You'll also notice that the toUpper is not supported by select. Instead, this portion of the query will be done on the client side. And if you have a large number of columns in the table and you're only selecting the ones you need, then this will save a sizable amount of unnecessary network traffic and will also reduce the total download and processing time for your operation. Another nice thing about the Azure Mobile Client API is that it's fluent. You can create a query, cache it off, and then modify it or add it with additional methods, and each method returns a new altered query. And in this case, we make 3 different queries: all, skip 5, and first 2. Remember, it doesn't actually execute until you enumerate it with one of the async methods. In our case, we're returning using the toCollection async. And when we execute the final query, all the prior queries are captured in the sent request, and you can see an example of that down the bottom. As mentioned earlier, you can also use the link syntax, and this is a language-specific syntax which looks very similar to SQL. And these 2 code blocks will generate exactly the same query, as there's no difference in performance or execution. The only difference really is the preferred syntax. So let's move on to Lab 3. Here we're going to add some database operations to our app and see it actually interact with Azure. Again, let's pause the video and then follow the instructions and then resume the video once you've finished. In this lab exercise, we're going to continue our modification of the Xamarin Forms app for the survey system. And there's a few things that we're doing here. Obviously, we've got our mobile service client, but this time we're actually creating an iMobile service table, one for the questions table and also one for the response. And you can see in our initialize call, this time when we're setting it up, we're actually getting a reference to those tables as well through the use of the client.get table, passing in the appropriate DTO to get the corresponding table reference. So you can see I've got my questions table and now my response table. And now I can actually use those in my various methods of this particular interface. So if I look at my add or update survey response async, I'm actually adding some logic here. If I've got my ID being null or empty, then I'm going to use the insert operation. Otherwise, I'm going to actually perform the update there instead. And likewise for things like the delete, it'll actually delete a particular record. And for the get questions, it'll get from the questions table all the records. It feels very similar to the SQLite.net mechanism that you might already be comfortable with, that you might have learnt in the SQL160 class. So lots of similarities there. And also for our get response for survey async, we've got some parameters being passed in, and we're using those parameters to just create a filter, and we're using that to get our result. Likewise, the get responses for survey async, doing the initialize call and getting the correct data. So this time, when we actually go ahead and run the application, and I might just change this over to iOS just for a second. We'll change it to the iPhone simulator. I might put it on an iPhone 7, and we'll go ahead and create it. We should actually see the results, and we should be able to connect into that Azure service and see the data coming back and actually send some data back with it. There we are. So it's connecting to the service, and we've got some options. Let's put our name. I'll put Judy's name in. Where should we have lunch? Let's just go Olive Garden. That'll be fine. Another question: which mobile platform do you like better? Well, I'll probably say iOS in this particular case. And I can look at the survey results and actually see the details that are coming through as well. Lots of great access there. And all we've really done is replace that service. So at this stage, if you've been following along, congratulations, you've actually got an Azure app. Delete is an interesting operation when dealing with cloud-based databases. It's destructive in that it removes records from the shared data source, which can then affect other clients working with this data. As a result, it needs to be treated specially, just to ensure that it's propagated to each client. And there's two ways to deal with this, and Azure supports both approaches. First, we can just delete the record and report errors back to clients who think the record is still there. Or secondly, we can use a soft delete model, where records are never actually deleted, but they're instead notated to indicate that they're no longer present. And that's the purpose of the deleted flag that we saw earlier in the JSON. And this is a column on every table exposed by a mobile app service. And the field is always present regardless of whether soft delete is supported, and it'll always be false if soft delete is not supported. So this soft delete approach is a requirement to effectively support offline synchronization, and the server decides on a table-by-table basis whether to turn on soft deletes. And the client actually doesn't have any control at all. If you do have soft delete supported by the server, the client can then use two other features that are exposed by the client SDK. First, you can see deleted records. These are actually not returned by default. So you can add the include deleted Fluent API to your query just to include records where the deleted flag has been set to true. Second, you can undelete records, restoring them to the live data. And this is done by retrieving a deleted record and then passing it to the undelete async method. You can actually call this on live records too. It just won't do anything because the outcome is going to be the same. We're just really saying that the record is no longer deleted. Finally, almost all of the table methods have multiple signatures. The second version supports a dictionary as input, and this dictionary is used to send additional parameters to the HTTP query in the form of key value pairs. And this is really useful if you're using the ASP.NET backend and looking for some additional data to be passed. So as an example, the deleted option just simply adds the URL parameter _include deleted equals true. Now we've gone through a lot in this section, looking at how we can get access to records through the use of Azure. We've defined the data transfer object, we've added new records to the database, as well as doing a lab that had us connect directly to an Azure service. Let's add one more feature to our application, offline caching and synchronization support. Now there's some very good reasons why you want to have offline synchronization in your application, and in this section we're going to take a look at them. So we'll add support for a local cache for those times when we're offline, and then we'll do the work to perform the synchronization to the local database. Mobile devices are so flexible in part because they're portable. You can take them with you. However, when you're dealing with a network resource such as a cloud-based database, that portability can also be a limiting factor because we don't always have network connectivity. So when you can't connect to Azure, or worse, the network drops out while you're talking to Azure, you have two options. First, you can catch the network exception and present a failure to the user and let them know that the app is no longer functional until network connectivity is restored. Or, second, you can provide some sort of support to work with the data offline until network connectivity is restored. And the option that you choose is really up to you, and to some extent, the data that you're working with. Sometimes you just can't allow users to work with data locally. Perhaps the logic is all server-side, for example. But often, this second option of continuing to work offline is an appealing one, except for one problem. First off, it's hard work. It's also a lot of effort, and it also becomes very complex. So it's actually such a challenge to mobile developers. We actually cover the thorny problem that is data synchronization in detail in our Enterprise 410 class and show you how to implement it in your app. But luckily, we're using Azure as our backend service here, and it turns out that Azure has really solved this problem for us. With a few lines of code, we can add support into our application to provide a locally cached version of a given table. And this support has a number of benefits. When we need this feature, our app will interact with the local database rather than waiting for Azure to respond. And that means local queries and changes all happen immediately, and you don't have to wait for network input-output to complete. And that in turn improves the performance of your application as it interacts with the table. And this can also mean that if the network is unavailable or even fails during an operation, your app continues unaffected. And you can continue to read and update the records that you know about. And then, when network connectivity is restored, the client SDK pushes any changes made locally up to Azure. Inserts, deletes, and updates are all sent in the order that we perform them locally. It also goes in the other direction too, and it will pull down changes made to the cloud database by other clients and synchronizing them to our local copy. So if the idea of automatic synchronization when the network is restored scares you a little bit, rest assured that you can control when synchronization occurs and also which direction it occurs in. This can be really helpful for high-cost networks or when the device is on domestic or international roaming. Now, before we turn on offline synchronization on every table, we really do need to ask whether or not we need it. And often the answer is a resounding yes, but there's also a few factors you may want to consider. First, adding a local cache adds security, storage, and network requirements to the application. And the entire table is cached locally on the device. And if it's really large or has confidential data in it, that may not be ideal. Records are not immediately written to Azure, but are instead cached locally and then pushed up to Azure as an async task. And these changes are often held locally in a database until they can be synchronized to the server. And often, when you have records like this, you often need to let the users know that not all the data is synchronized either. Maybe noting that there are changes left to synchronize through a badge icon on your app, like the Mail app does, or maybe you update the user interface in order to inform the user about the unsynchronized changes. If the data you're working with doesn't change very often, or even better, is read-only, and you can simply pull it down once, then you can just read the data at startup, store it on your own, possibly encrypting the data, and then use your local cache on your own without using the Azure offline support. To add support for offline synchronization, you'll need to add another NuGet package. This time, it's the Microsoft.Azure.Mobile.Client.SQLite storage package. This package sits on top and includes the Mobile Services Client SDK to connect to our backend and adds full online-offline synchronization. So just like with the core package, you should add this to all head projects and to any project that will utilize any types in the Client SDK. And this package adds all the required assemblies to keep a full copy of a table locally on the device. To support a local copy of a table, the Azure client will use a locally installed database. It'll then download the Azure database and create a local cache of the data on the device. And by default, it'll use SQLite, a popular open source database, as the local database. Now, we cover SQLite in our AZR115 class, but you don't actually need to know anything about the storage beyond a few methods to set it up. And the Client SDK takes care of all the steps necessary to download the database and store it in SQLite. And even though SQLite is the default, as you'll see in a moment, the client support is actually quite extensible, and you can replace the local storage with something different if you need to. For example, native iOS applications use core data, not SQLite. iOS and most versions of Android have a pre-installed SQLite engine as part of the ROM image. So in cases when it's not available, the SQLite NuGet package installs will actually include a runtime binary for the database. However, Windows doesn't, and the PCL NuGet requires that you add the SQLite binary reference to your platform-specific Windows projects. And these are SDKs you download into Visual Studio using the Tools, Extensions, and Updates dialog. So you should install each package that you'd need. And there's 3 of them which are relevant to most developers wanting to target Windows. There's the Windows Runtime 8.1 for Windows 8.1, Windows Phone 8.1 for Windows Phone 8.1, and UWP for UWP. Once you've installed the SDKs into Visual Studio, you'll need to add a reference to the library in your Windows head projects. And this is done through the Add Reference dialog. So select the Extensions section, like you can see here, pick the SQLite Runtime Engine support, and then this will include the native C++ engine into the application. And it also means your Windows applications can no longer be built for any CPU. Instead, you'll need to change your build configuration to use either x86 or x64. As mentioned before, iOS has a built-in version of SQLite. However, the PCL client library we'll be using requires that you initialize it as part of the application initialization. And this is done through a single call to current-platform.init, which should be part of your app init sequence. So a good spot for this is when you initialize your Azure client library, typically in the finish launching method of your app delegate. And this is actually only a requirement for iOS. Android and Windows don't need this at all. And this is also true for your iOS Forms target apps as well. So make sure to add this line into the iOS specific project there. Before we get into the mechanics of how to activate and use offline synchronization, let's quickly examine the players. The remote database is the master store of data on Azure, and we've already worked with that in our AZR110 class. The local database is where we store a local copy of the table and also where the local changes are kept until they're synchronized with the remote database. Each table we keep an offline copy of will have a synchronized table interface we use to do queries, update data, and push our changes up to the remote database. Our old friend, the mobile service client, also has a role here too. It has a property on it named synContext, which we've not set up or used yet. And this is actually where the real magic happens. A synContext is associated with a mobile client object, such as an iMobile service client, and then tracks changes that are made with sync tables. The synContext maintains an operation queue which keeps an ordered list of create, update, and delete records that will later be sent to the server. So the synchronized table objects know about the associated synContext and write local changes made to the local store to the operation queue to be pushed to the server. And your code will use the synContext property to pull remote changes back to all the local tables. So let's look at what it takes to activate an offline cache for a table, and we'll need to do 4 steps. First, we'll initialize a local SQLite database to be used as our local cache. Then, we'll associate this database with a created mobile service client. Next, we'll retrieve a synchronized table from the mobile service client. And this is similar to the table interface we used before, but it includes support for an offline cache. And we will do this step for each table we're going to keep an offline copy of. Finally, we'll use this new synchronized table interface to read and write our data locally and synchronize with Azure. So let's have a look at these steps in detail. The first step is to set up a local store used as the data persistence layer on the client device. And the client SDK provides a default local store implementation based on SQLite. And you can also implement your own local store. For instance, if you wanted to store data in an encrypted format on the mobile client, you can define a local store that uses SQL Cipher for encryption. Now today we're just going to use the default. So here we're going to create the SQLite store. So we create a new table store object, mobile service SQLite store. And we pass in a file name, which will be the created file on the local device to hold the database. And you can call your store file name whatever you want. It's a local database store, and there's really only one per app. Next, we need to define each table we want to store in the local database. And this is done through calls to the defined table with a generic parameter, where that generic parameter is the DTO. And you can also pass in a JSON object, which can then be used to infer the shape of the data. And if you need more than one table, just add additional defined table calls. And the local store object will examine the DTO or JSON block and then generate a SQL table in the local SQLite database to hold data for that object. Finally, we need to associate the local database storage with a mobile service client through its built-in synContext property. We have to call initialize async and pass in the local database store, and this is what activates the local caching support. And you should notice that this call is asynchronous, and this is what executes the database initialization code, opens the SQLite database, and if necessary, creates the table in the local database. The second parameter is a sync handler class that's used by the context to process table operations as they're synchronized to the server. So the passed object must implement an interface called iMobile Service Sync Handler. And this is really just an extension point into the Azure client framework. It includes methods like execute table operation async to execute a single table operation on the Azure remote table, and another method on push complete async, which is called when the push operation completes to do post-processing after the push completes. The Azure client implements a standard class that essentially does nothing, which we're using here. It just executes the operation asynchronously and does nothing when it returns. And you can also look up the source code to this on the GitHub repository. Now, we mentioned before that you can provide a different database storage technique. And the way we would do that is to provide a different implementation of the database store to the synContext.initialize method. Now, the local store is just an interface that you can implement with a set of CRUD methods. So here we've got an example XML store that we might want to use. So you can also derive from the built-in abstract class mobile service local store to get a partial implementation. Now, Everything is set up to support offline caching. We just need to use the correct implementation of our table interface. So remember that we used getTable to retrieve the table interface for a live connection. So when we want to support a local cache, we won't use getTable. Instead, we're going to use a variation of that method called getSyncTable. So there's also a non-generic and generic form of this method as well. So the same rules apply. And this method returns an iMobile Service sync table interface, which replaces our original iMobile Service table. Using the iMobile Service sync table should be an easy transition. It exposes the same methods used on our original table interface. For example, here's our code to insert a new entry into our diary table. And the big difference with this implementation is the code will continue to work even if we lose network connectivity. Well, let's now move on to Lab 3. So here we're going to add some database operations to our app and see it actually interact with Azure. Now again, let's pause the video and then follow the instructions to add offline data caching support to our application. And once you've finished the exercise, resume the video and then we'll review it. Now for this lab, we're actually going to implement the offline support. So there's a few things that we need to do. Now first off, we actually need to add a new package into the mix as well. We need to add the Microsoft Azure Mobile Client SQLite Store. And you can see that package is added there, and that'll actually help with the offline support. We'll see how it integrates in a little bit later. But just like before with the previous package, you have to add it to your shared code, and you also need to add it to your platform-specific host projects. Now also, if you're using iOS, and actually 2.x versions of Azure Mobile Client, will need to call SQLite PCL current platform.init. Version 3 actually doesn't need this anymore. So if you're following along with the labs and you realize, actually, that's not working, just remove that line. It's actually working in Azure Mobile Services version 3 and above. So what you need to do after that is we change our references where we have the questions table and the response table from before. We actually use the iMobile Service sync table. And in addition to that, our initialization is a little bit longer. First off, we're creating the backing database store, the Mobile Service SQLite store, and you're passing the location of the database. Interestingly enough, on iOS, this will actually put it in the Documents folder. You may actually want to change that folder to the Library folder for iOS to get that to work correctly. Then in that store, you want to define the tables that it will store the DTOs, in this case, the survey question and the survey response. We then create our mobile service client as before, and then we initialize our client using the client sync context, initialize async, passing in the store, and passing in the class that's going to handle the synchronization between your local data and the Azure data. That's the mobile service sync handler. And then we get the references to the tables, the questions table and also the response table. In this case, we're calling client.getSyncTable, not getTable, and passing the generic parameter that represents the DTO. So then, in order to use the service, we'll also need to tweak the calls in each individual method slightly. Before, we were just returning the task directly. This time, we'll need to actually await a particular operation. We need to await the initialize async. That might actually take a little bit longer just because of all the async calls that need to occur here. So especially in regards to the initialize async while it sets up the database. Here we've basically got the same logic. We're just awaiting on the operations and we're marking each method as async. So this time, if we go ahead and run the application, let's do this again. We should see the application run. So it's running, it's got a connection to the offline data, but we actually have no data at this stage. We've got a little bit more work to do, which we'll do in the next lab exercise. Now let's look a little bit deeper at the architecture and interactions between the players. When you perform table operations on the iMobile Service sync table, such as an insert operation, it delegates these to the associated mobile service sync context, which in turn pushes those changes to the mobile service store, in this case, our SQLite implementation. So the database store will make those changes to the local database on the device. It will also record the change to a pending operation queue stored on the same database. You then decide when those changes are pushed up to the Azure mobile app backend by calling iMobile Service sync context.pushAsync. And this is the sync context on your mobile services client. So push is an operation on the sync context and sends all create, update, and delete changes since the last push. And it's not possible to send only an individual table's changes because otherwise operations could be sent out of order. Push executes a series of REST calls to your Azure mobile app backend, which in turn will modify the server's database. And this will retrieve the pending operations from the local database and send them one at a time to the remote Azure database using the table endpoint. So it uses the same operations we use with the live endpoint: post to add new records, patch to update, and delete to delete. Finally, if a record has multiple modifications against it locally, it was inserted then updated multiple times, only the final state of the record will be transmitted to Azure on a push. It will not be pushed multiple times. Push async will push our changes to Azure, but we also have to pull remote changes back to our local database, and this will update our local copy of the database with any changes performed by other clients. And we do this on a table-by-table basis by calling the pull async method on the sync table object. This will use the mobile service client to retrieve all the entries from the remote database. It then writes those records to the local database cache. One optimization we can do with the pull API is to enable incremental sync. And to turn this on, we pass a string parameter called a query ID to the method. And by supplying a value for this, the client will keep track of the last time the specific query ID was issued and then only pull down data changed in Azure since then. It uses the updated at column that Azure automatically puts onto every table, and only records with an updated at value greater than the last synchronized record will be retrieved from the back end. You can see the query here, and notice that the updated at filter is being applied automatically. There is one more optimization that the client SDK does to try and help out on unreliable networks. Rather than trying to pull all the data down at once, it does it in chunks. In both the incremental sync and full sync, the client API requests the server records in 50 record chunks. It continues to request pages until the server returns less records than requested to ensure it gets them all. So each chunk is then written to the local cache. As you've seen, the synchronization mechanism is a manual trigger, and the code is all done for you, but you have to cause it to happen. So the synchronization process is asynchronous. It won't block your user interface. And the recommendation is to perform a full synchronization when your app first starts up, and then each time you make a change to the local database. Here we've created a local method to do the push-pull, and we call it when we update a diary entry. The synchronization method performs the steps necessary to perform a synchronization. So let's walk through the steps. First, we can do an upfront check to see if we have network connectivity using the cross-platform open source connectivity plugin. This is a single call to detect whether we've got a valid network connection. And we cover this in XAMRR115. And this step isn't actually necessary, strictly speaking anyway. However, the actual network input-output will fail and throw an exception if we don't have a network. It's more efficient to test for connectivity before attempting to do the network call. Next, we push all our local changes up to the remote Azure database. And this is done through the sync context push async method. And it pushes all create, update, and delete operations that were done to the local store up to the server. And it uses the same REST endpoints used by the normal table interface. And this is also the most common point of failure when synchronizing to the database. So you should always execute this method in a try-catch. And it will throw an exception if the modified record version doesn't match on the server side, and that indicates that a different client changed the same row. Next, we pull new and change records for each of our synchronized tables. And remember, this is a table-by-table operation, so you'll need to have one call per synchronized table. And records that were changed locally are not returned. And this is done by calling the pull async on the sync table object. If a pull is executed against a table that has pending local updates, which haven't been synchronized, the pull will first execute an implicit push on that sync context. And this helps to minimize conflicts between changes that are already queued and new data from the server. Now it turns out that the call to push async is redundant in this case. If a pull is executed against a table that has pending local updates, which haven't been synchronized, the pull will first execute an implicit push on the sync context. And this helps minimize conflicts between changes that are already queued and new data from the server. The second parameter passed to pull async is the query used on the server side to pull the records. And you can pass create query to return all records, or provide a custom query to retrieve a subset of records from the server. and the sync context will then insert the return data into the local store. The first parameter to the pull operation is a query ID that's used to identify the query on the client. As mentioned before, if you use a non-null query name, the client will perform an incremental sync, where each pull operation returns only the records changed since the last pull. The updated app value is cached off, and subsequent pull operations will only retrieve records after that timestamp. And the query name can actually be any string you choose, but it has to be unique for each logical query in your app. Otherwise, different pull operations could override the same incremental sync timestamp, and your queries can return incorrect results. You should also really only have one query per table, ensure that the query operations encapsulates the data that you want to retrieve. And that makes incremental sync work the most efficiently, and it takes up less CPU and memory overhead in your client. You can also pass null as the query name to turn off incremental async and pull all records that match the query. But this is suboptimal since it pulls records that haven't changed. You can clear the contents of the local store using iMobile service sync table.purge async, and this might become necessary if you have stale data in the client database or if you wish to discard all pending changes. And a purge will clear a table from the local store. If you want to just remove a specific set of records from your local database, you can pass a query into purge async just to be a little bit more specific. The other case where purging your local cache becomes important is when records are deleted on the server. If soft deletes have been enabled on the server, then the synchronization process will detect these deleted records and delete the local copy. However, if soft deletes are not enabled on the server, then deleted records will remain in your local cache even though they're not on the server anymore. So just like push async, calling the purge method will push any local modifications first before it actually purges the local store. So it's time for another exercise. This time we're going to be synchronizing to the remote database. So just like before, pause the video, do the lab, and when you're finished, resume the video and we'll review the lab. In this exercise, we're actually going to add the ability to pull down records from the server and actually synchronize those changes or any changes that we've done back to the server as well. In our last lab, what we had was the Azure infrastructure where we could actually call into the service. We weren't pulling any of the information down by default. Now, at the end of this initialize method, you can see in this exercise, we're doing a couple of things. First off, we're using the cross-connectivity plugin. It checks to see if we have a network available, and if we do, that's when we do the work to actually download the information. So the push async will actually send all the changes back to the server, and the pull async will bring down the records down to our local device. You'll notice in the other methods as well, you can see we've got the synchronized responses async. So that'll actually perform the synchronization to and from the server. That'll issue a pull. And you can see when we're doing things like the add or update survey response async, we're updating the data just like we were doing before, but we're following that up with the synchronized responses async. So every time we make a change, we're doing a synchronization to the server. Supporting offline updates is pretty cool, but there's some inherent risks in this model. For example, you've got issues like when you're offline, a client might change a row, and sometimes they might push the changed record to Azure, but the rows have been changed by someone else. You might have the situation when the client makes a change to a row that causes a constraint failure in the remote database, so you get an error, and so that update can't apply. Or when you're offline, some other client deletes a record, and the app tries to push that delete to Azure, and it finds the record was changed by someone else, a classic synchronization problem. So up until this point, we aren't seeing any of those problems, and that's because we've not turned on support for conflict resolution. As a result, every change made simply overwrites the server's copy indiscriminately, and we don't even know about it. Now the problem is, once we activate the built-in conflict resolution support, then all of these will result in a client-side exception. However, that's actually a good thing because then we know we've got a problem, and Azure sends us all the details, and we just need to decide what to do. So let's look at the process of resolving the conflict. To turn on the automatic conflict resolution, all you need to do is add the version property into your DTO. And remember that this is a system column. The reason Azure doesn't notice the conflicts today is we aren't sending the version with our updates, we're only sending the required fields. By mapping this column into our DTO, we capture it as part of our data, and it can then send it back to Azure, and we make a change. And then Azure can compare this model, which changes each time someone updates the row against the server-side version. So if they're different, it notifies us about the conflict. When this happens, the Azure service will return a HTTP error response as the result of the conflict, returning both the client record as well as the server record.
So the client SDK can then turn this error response into a .NET exception, which then your client code has to handle. The exception type is a mobile service push failed exception, and it contains all the failure details of all the conflicts that have occurred as a result of the push. And inside this exception is a list of the table errors. Each one describes a single update failure. So the client just has to walk through this list and really just decide what to do for each conflict. Each conflict error is represented by a mobile service table operation error object that contains the details about your conflict as well as both the client and the server DTO, so you can decide what to do. So here's an example on the screen. Here we're walking through each error and calling a custom method to resolve each conflict based on the error. And notice that our custom method is async. This is because the response to a conflict will often involve sending the server another update by merging the client and server record, or by simply replacing the server record with the client's version of it. And that means a network round trip. So we tell the server what we want to do by calling a method on the mobile service table operation error. Once you detect a conflict, you have a variety of ways you can handle it. You can decide that the latest update is the correct one. You can tell the user and let them pick the version they want. You can try to merge the two or have the user do it, or you can decide that the server is always right. The mobile service table operation error really includes 3 methods on it for selecting each of these options. The first operation, cancel and discard item async, removes the changes that you made to that record and then updates that record to the initial version. The second operation, cancel and update item async, removes the update that you wanted to apply and updates your copy of the record to one on the server. And the last operation in the list is to update the item with a new version and then try to synchronize that entry with the server again. In this example, we assume that we always want the latest client version to be used. Let's have a look at how it works. First, we take the server and local item and compare the custom fields, ignoring the version and update data information. If they're the same, logically not the same reference, then we can ignore this conflict, and the other client made the same change, so we can call the cancel and discard item async. In this example, we're comparing the text property, but you'd probably have a more rigorous check for equality. Otherwise, we'll take our version over whatever the server has. So we need to copy the version data and then resubmit our change to Azure. And this will also update our local object in our local database. There's one more exercise in the lab materials, which is to really add error recovery so we can support conflict resolution. And we've really added it normally in our in-class classes as a homework exercise, but because we're doing a video, let's actually go through it today. So the same rules apply. Just pause the video, and when you're finished, come back and we'll review it. Well, for this last lab exercise, what we're going to do is implement the conflict resolution. So there's a couple of things that we need to do. First off, in our model class, in this case the survey response, we need to add the version. So we're adding the Azure version into our list. Now, the next thing we need to do is we also need to catch any exception during the synchronize process. And you can see in the synchronized responses async, we've got a try catch, and we're using the mobile service push failed exception. So when that occurs, then we've got our list of conflicts. And we can actually look, if there's the push result is not null, then we can have a look at that push result, look at the errors, and then for each of those errors, we'll actually resolve it. And you can see it's being delegated to this resolve error method. We'll just scroll down and we'll actually look at the logic there. So you can see we're getting the server item and the local item, and this capital result is the one that's on the server. The local item is our item, so that's the one from the mobile client, and we want to compare those and actually decide what we need to do. In this case, we're checking if the names are equal and the response index is equal and the survey question ID is equal as well. Then we'll just cancel and discard the item because essentially they're the same. Otherwise, we're taking the rule that we always want to take the client. And then after we've got the client, then we'll actually perform the update operation async. And of course, you can apply your own logic and rules to match your particular business requirements. So that's our look at offline synchronization. We've looked at the benefits, we've seen how to use local SQLite storage, we've set up that local cache, you've also had a look at some of the other mechanisms around it, also things like the conflict resolution as well, and how to synchronize to that online database. A lot of great technology in that Azure stack. Probably the next best thing is to start building your app. But this video recording, well, it's made in October 2016, and we've got lots of Azure courses in the pipeline, And we've already announced that we'll be delivering 3 courses very soon. And that includes the Azure 120, which is to add authentication to your Azure mobile apps. And that's where you'll learn how to secure your Azure backend service and its data and authenticate from the mobile client using OAuth. There's also Azure 130, supporting push notifications with Azure. So you'll dive into the Azure Notifications Hub, explore how to utilize this cross-platform API to send push notifications to your iOS, Android, and Windows devices from a single API. And lastly, we've also got our Azure 140 course coming too, and that's for building web services for your Azure mobile app clients. In that class, you'll explore the web API features of Azure App Services to create custom web endpoints your applications can consume to execute algorithms or CPU-intensive operations in the cloud. Also, if you're a developer that builds their applications using MVVM, keep in mind that in our labs, we have a completed solution of the product built with the MVVM style. So a big thank you to everyone for watching this video on creating Azure mobile clients with Xamarin. My name is Glenn Stevens, and I hope to see you in our live classes or when you're watching the videos. Until next time, goodbye from Xamarin University.